Hello. Let us now consider the equilibrium of a body under the actions of an arbitrary three-dimensional system of forces by the example of a turbine spindle. In mechanisms to be used for wind and water energy conversion, tooth gears are used, which transmit rotation from one spindle to another. It can be seen from the following examples: a water turbine or a wind motor. Let us draw up a sketch and make the statement of a problem. A force couple rotating a turbine is balanced with the pressure on a tooth of the bevel gear wheel and with the bearing reactions. The pressure on a tooth is perpendicular to the radius and makes an angle of 15 degrees with the horizon. The reaction of center plate and the reaction of bearing are required to be found. Let us consider the equilibrium condition of the spindle with the turbine. Let us draw up a free body diagram. To this end, we replace the constraint forces with the corresponding reactions. A constraint for the spindle in the center plate, and we resolve the reaction force of the center plate into three components: XC, YC, and ZC. The bearing in the point A is also constrained, and we resolve the bearing reaction into two components: XA and YA. The bevel gear wheel is also a constraint, which we mentally remove, replacing its action with the corresponding reaction. Apart from the reactions of the constraints, the gravitational force is also acting on the turbine spindle. Thus, we have obtained a balanced system of forces: XC, YC, ZC, XA, YA, Q, P, and a couple of forces: F prime is also included. Under the given system of forces, the body is in equilibrium, so we can write down 6 equilibrium equations. The sum of projections of all the forces on the axis x must be equal to 0. The sum of projections of all the forces acting on a given body on the axis y must be equal to 0. The sum of projections of all the forces acting on the body on the axis z must be equal to 0, and 3 equations for the moment. The sum of moments of all the forces acting on the body with respect to the axis x must be equal to 0. The sum of moments of all the forces acting on the body with respect to the axis y must be equal to 0. And the sum of moments of all the forces acting on the body with respect to the axis z must be also equal to 0. An easy way to write down the equations is to resolve the force P into components Px and Py, Pz. The magnitude are Px equals P multiplied by cosine alpha, Py equals P multiplied by sine alpha. Let us write down the equilibrium equations as XA plus XC minus P multiplied by cosine alpha equals 0. YA plus YC equals 0. Minus Q plus
ZC
ZC minus P multiplied by sine alpha equals 0. Now that we have 3 equilibrium equations written down, we need 3 more equations for the moments of forces with respect to the axis. Let us write down 3 moment equations. The moment of the components xc, yc, zc, and xa with respect to the axis x is equal to 0, because the lines of actions of these forces cross or are parallel to the axis x. The moment of force yc with respect to the axis x is equal to the product of the force, magnitude, and the distance from the force's line of action to the axis x. The moment is written down with a negative sign because as we look towards the axis x, we can see that the force yc is tending to rotate the body clockwise. The moment of force P is equal to the product of the magnitude of the axis C component and the distance from the force's line of action to the axis Z. This distance is equal to r, and the moment can be written with the positive sign, because the component PZ is tending to rotate the body counterclockwise. Let us write down the moment equations with respect to the axis y. The moment of the components xc, yc, zc, and ya is equal to 0 because the lines of actions of these forces cross or are parallel to the axis y. The moment of the component xa is equal to the product of the magnitude xa and the distance from the force's line of action to the axis y. The moment of the force P is equal to the product of the magnitude Px and the distance from the force's line of action to the axis y. The distance is OC. And the third moment equation with respect to the axis Z. The moment of the force couple is perpendicular to the plane in which the force couple is lying and is directed along the axis Z. The moment is in the same direction as the axis, therefore it's written with the plus sign in the moment equation. The moment of the force P with respect to axis Z is equal to the product of the magnitude of this force projection on the axis X and the distance from the force's line of action to the axis Z. Sign. We look toward the axis Z and see that the component Px is tending to rotate the body clockwise. Therefore, we write it in the equation with a minus sign. So we have 6 equations with 6 unknowns. We have the following known values: xa, xc, p, ya, yc, and zc. Substituting the numerical values, we then determine the unknowns and also the reactions in the points A and C, which are determined as the square root taken of the sum of squares of its components.